Well, hello, everybody. Welcome to all of those who are joining us today for our weekly virtual field trip program from Cooperstown, New York, site of the National Baseball Hall of Fame and Museum. Glad you could join us. For those who don't know me, my name is Bruce Markison. I work in the education department. Our program this week, our theme this week, is called Circling the Bases, Baseball and Geometry. We're going to examine how basic geometric concepts like circumference, area, perimeter, diameter apply to baseball and the real world. We're going to analyze characteristics of the baseball playing field and interpret data using really fundamental geometric ideas. And we're going to understand characteristics of shapes that we can find in the game and how we can use these shapes to or how we can apply these shapes by using geometry. So that's what we're going to do today. Now, what we like to do before we actually begin with the content of our lesson, we like to give you a quick virtual tour of the Baseball Hall of Fame. So you should see on your screen right now a picture of the museum from out front on Main Street. The museum is currently closed, although we're all hoping that's going to change in the coming weeks. We just don't know when at this point. Three-story red brick building that officially opened back in 1939. Where are we geographically? We have folks joining us today from all over the country: West Coast, East Coast, Central part, Midwest, probably the South as well. We are in the Northeast. You can see here a map of the United States. You can see Pennsylvania, New Jersey, Connecticut, Massachusetts, New York State. And if you look at New York State, there is a reddish or orange arrow pointing at what looks like an American flag. It's actually the Hall of Fame logo. It's got a baseball in the middle. And that is where Cooperstown is. We are in what's called upstate New York or central New York. And we are about a 4-hour drive from New York City. Now, of course, New York has 8 million residents. Well, we're slightly less than that here in Cooperstown. We have only 1,800 people who live here on a year-round basis. We are very much part of rural America. This is what Cooperstown looks like. It's a great photo from a typical summer day here. Our beautiful lake, Lake Otsego. Lots of trees, rolling hills, and you will not find any skyscrapers here. Our tallest building, the Otesaga Hotel, is all of 5 stories. Now, I mentioned we have this really pretty small population, 1,800 people living here year-round, slightly more than that during the summer months. But with the population being this small, we have need for only one traffic light. There you see it. It's at the corner of Main and Chestnut Streets, and that's it. And most of the year, one traffic light is all we need. Now, we do typically get some big crowds during the spring and summer. If you look at the upper half of your screen, that is a picture of historic Doubleday Field, which celebrates its 100th birthday this year. Yeah, it was built in 1920. It's currently under construction. They're doing some renovation, scheduled to be reopened later this year. Don't know exactly when. But it's going to look really nice. They're going to add some clubhouses. They're going to add kind of an observation deck, make some other needed improvements to the stands. So that's one of our venues where we typically have pretty large crowds. The bottom half of your screen is a picture from our annual induction ceremony. And typically that is toward the end of July, usually the final weekend in July. And it's an event that has drawn, tens of thousands of people over the years. This is the biggest crowd we ever had in Cooperstown. This was 2007, when 2 really popular players, Cal Ripken Jr. and Tony Gwynn, were inducted into the Hall of Fame. They were so popular, they drew an estimated crowd of 80,000 fans. That's what you see in this overhead photograph. And right now, that's our record. That's the biggest crowd we've ever drawn to town. Now let's go inside the museum. Here is our Plaque Gallery, which is really the centerpiece to the Hall of Fame complex. This is where we house the 329 bronze plaques, which represent each of our Baseball Hall of Fame members. And when I talk about Hall of Fame members, these Hall of Famers, I'm talking about the greatest players, managers, owners, executives, umpires in the history of the game. Really the best of the best of the best are represented here in Cooperstown. It's an exclusive club. Now, if we head up to the second floor, one of the first exhibits you'll see is this one, Taking the Field, Baseball Before 1900, and it examines the origins of baseball. How did the game get started? When did it get started? And trying to trace baseball history can be a little bit complicated, but we have actually found a reference to the game in 1790 in Pittsfield, Massachusetts. So we know that here in the United States, baseball goes back at least that far. But it was not until the 1800s that the game really started to become popular and really started to take hold in American culture. Now, as we moved into the 20th century, here's a guy who became one of the game's early superstars, George Herman Babe Ruth. We can get into all kinds of debates about who the greatest player in baseball history is. Some would say Babe Ruth, others would point to another player. But I don't think there's much debate about who the most famous player of all time is, and I think that's Babe Ruth. And it's one of the reasons why we have an entire room dedicated to his career and his life. Everything in this room is connected to Ruth. There's photographs, there's film and video, there's artifacts, including a uniform that he used to wear. It was after his playing days, but whenever he made promotional appearances, he wore that number 3 uniform that you see on the left side of your screen. One of our most important exhibits, Pride and Passion, is all about the history of African Americans who have played the game. You know, there was unfortunately a time when baseball was a segregated sport. There actually was a color ban in place from 1887 until 1947. And during that time, no teams signed African American players, no major league teams, and most minor league teams didn't either. But it started to change in 1947. The Brooklyn Dodgers signed Jackie Robinson, and you can see his Brooklyn Dodger cap in the lower left-hand corner. And he was so successful as a player that he basically opened the door for other African American players, many of them coming from the Negro Leagues. The Negro Leagues had been set up as part of this segregated situation in baseball. White players only were allowed in the majors. So Rube Foster started what we now call the Negro Leagues in 1920. And with Jackie entering the scene in 1947, that would finally start to change. Might also notice the ticket. It says colored on it. This was a ticket from a minor league game in Eastman, Georgia, 1953. And it was a game where they would sell, stadium where they would sell tickets based on the color of the skin of the fans. So if you were white, you would be sold a ticket. You would sit in one section of the ballpark. If you were black, you would be sold a ticket that said colored, and you would have to sit in a different section, probably in the outfield, probably where the seats were not as good. And segregated seating actually continued in baseball even into the mid-1960s, even after the Civil Rights Act was passed. Now, some people will tell you that baseball is a game for the boys, and if they ever tell you that, you can correct them and say that's not the case. The fact of the matter is that girls and women have been playing organized baseball since the 1860s, 150 years ago. The first organized team was at Vassar College, which is a college in New York State, not that far from here in Cooperstown. There have been teams like the Bloomer Girls. There have been leagues like the All-American Girls Professional Baseball League. So their stories are told in this exhibit, Diamond Dreams, one of our most popular exhibits during the summer months. Our newest exhibit here at the Hall of Fame opened up less than a year ago. It's called Shoebox Treasures. It's all about the history of baseball cards, card collecting. It's one of our great American hobbies, and it's a hobby that I enjoy as well. So we examine the history of baseball cards in this very interesting exhibit up on the 3rd floor. And also up on the 3rd floor, we have an exhibit called One for the Books, all about baseball records and the stories behind them. And when we talk about records, we're talking about numbers, players who have set numerical records. You can look up who has the most home runs in baseball history, who has the highest batting average, what pitcher has won the most games. All of those records, you can find out who owns those records and the stories behind them in our One for the Books exhibit. And that's a natural transition to today's program on geometry, circling the bases. Here we have a scoreboard, Fenway Park, home of the Boston Red Sox. You know, if you show up late to the ball game and you're trying to catch up on what you've missed, the quickest way to do that, to get kind of the basics of what's going on, is to look at the numbers on the scoreboard. They tell you that the New York Yankees have scored 13 runs. The Red Sox have scored 2 runs. The game is in the 6th inning. And number 21 is at bat for the Yankees. The count on him is 3 balls and 2 strikes. So numbers help us figure out where we are in the game. They provide a nice summary of what has happened. Now, we don't know all the details. We don't know how the runs were scored and who's hit home runs. But we have the basics. We know who's winning. We know who's losing, what inning it is in, who's at bat, and what the count is. Numbers also help us identify players. Players can wear anything from 0, as Al Oliver once did. Al's a friend of ours. He's actually someone who posts on our education Facebook page from time to time. Great guy, very fine player, and he wore the number 0. But players can wear up to 99. 3-digit numbers are not allowed. Fractions, not allowed, although they were used once in a kind of a strange situation, but they're not allowed today. Decimals are not allowed. It has to be a whole number from 0 to 99. And if you go to a game and you match up the numbers to the players listed on your program, you can figure out who the players are. We can also use numbers to kind of map out the playing field, as you see in your upper right-hand corner. There are very specific measurements between the bases, from the pitcher's mound to home plate. There is a pitching mound that has a specific diameter. There are batter's boxes. There's a catcher's box. There's a home plate area. There's a coach's box. And we use numbers. We use math to measure all of these things. Now, here we have some very important playing fields for some of our more popular sports. In some cases, we can't really call them fields because they're not fields. They have different kinds of names. But you see 3 different sports represented here. I'm going to ask the students who are watching to take a look and see if you can figure out what the sports are. We're going to start with the one in the upper left-hand corner. Not a baseball field. That's actually a soccer field. And if any soccer fans are watching, they know that the soccer field is actually called the pitch, the soccer pitch. So that's the field for a soccer match. And you can see that there are circles, ovals, rectangles that have been mapped out on that soccer pitch. The middle field is a football field, and that is sometimes called the gridiron. It's kind of an old-fashioned term, but I still use it. Others do as well. And you can see the yard markers have been laid out here. There are end zones on the left and right sides, goalposts drawn in as well. So the football field, the gridiron. And then in the lower right-hand corner, we have a, not a field, but a court. It's a court from a sport, an indoor sport, basketball. And sometimes the court in basketball is referred to as the hardwood. It's a basketball court. And it also has some shapes that have been drawn out, that have been measured. Circular shapes, rectangular shapes, half circles. Interesting things that have been drawn onto the basketball court or the basketball hardwood. Well, baseball has its own playing surface or field. It's a game that can be played outdoors or indoors in dome stadiums or retractable roof stadiums. Sometimes in baseball, we refer to the infield area as the baseball diamond. When you look at it from this angle, I guess it looks a little bit like a diamond. You know, you can see the 4 points of the diamond where the bases are on the infield. But if we're to be accurate, technically, it's not shaped like a diamond because a diamond has kind of inverted sides. No, this actually, if you look closely, this is a square. The infield is actually a perfect square. It has 4 sides to it. They're all identical in length. And there are right angles or 90-degree angles formed at each of the bases. So looking closer, yeah, this is technically not a diamond. It is a square. We don't call it the baseball square, but that's what it really is. It is a square geometrically. Again, we can take all kinds of measurements on the field. There's a distance between each base. That is 90 feet. 90 feet from home plate to first base, 90 from first to second, and the other bases is the same thing. From home plate to the pitcher's mound, it is 60 feet 6 inches. The pitcher's mound is a circle, and it has a diameter of 18 feet. You'll see the home plate area is circular. Within that circle, there are 2 batter's boxes, 2 rectangles on either side of the plate. Let's look closer at this home plate area. We'll find some shapes here. If you look in between the 2 batter's boxes, we've got home plate. It's a 5-sided shape. And we call that 5-sided shape a pentagon. It's a pentagon, 5-sided shape. Rectangles are 4-sided shape. We have a batter's box on the left-hand side, and that's actually for a right-handed hitter. So if you're a right-handed hitter, you would step into the batter's box on the left side. If you're a left-hand hitter, you would actually step into the box on the right side. A little confusing. But from this perspective, left side batter's box for right-hand hitters, right side batter's box for left-hand hitters. And then behind the home plate area, behind home plate and the batter's boxes, is actually a catcher's box. A lot of people are not aware that the catcher actually is supposed to stay within that catcher's box when the pitch is being delivered to him. Now, all of these different measurements and these shapes, these are all laid out by professional staff at Major League ballparks. There are 30 Major League teams, so 30 Major League parks. And they have staff that are trained in this. They have gone to college. They have taken classes specifically for the purpose of groundskeeping and properly laying out all of the features that we see at the ballpark. The batter's box is very specific. The baselines, you can see that they are laid out a straight line from third base to home plate, from home plate to first base. So you see those 2 baselines right there. In the lower picture, you can see one of the members of the Major League grounds crew is actually mowing the lawn, and in so doing is actually creating some shapes where the path of that lawnmower has cut. So these are all trained staff. They've all gone to some sort of a college, university, to specifically learn the art of maintaining and properly laying out a baseball field. Now, in addition to finding circles and rectangles, we'll talk more about that in a moment, on a playing field, we can find angles on a field. So here, if we look at the third base line and the first base lines, they meet at an angle. Now, the way the photograph has been taken, this is a little deceptive, but this actually is a right angle. It kind of looks like an acute angle just because of the angle of the photo. But this is actually a 90-degree angle that's formed at home plate, where the third base line and the first base lines meet at home plate. That is a 90-degree or a right angle. So that's what's seen here. What about those rectangles that I mentioned? Well, I talked about the batter's boxes earlier. There's the catcher's box. Also, if you look down the foul territory on the third base and first base sides, you can actually see 3 sides of a rectangle, and that's a coach's box. Coach technically is supposed to stay within the box at all times, but they don't actually do that. It's just sort of a guide for where they're supposed to position themselves. You can see the third base coach is a little bit past the box because he's concerned about getting hit by a foul ball by the right-hand hitter. So a lot of coaches will set up beyond those lines, but those are called coaches' boxes. They're rectangles. Now, when we look at rectangles, whether it's on a baseball field or just a rectangle in general, there are measurements that we can take. And one of them is the perimeter of a rectangle. And in order to figure out the perimeter, it's pretty basic. All you do is add up the length, the measurement of all four sides. Now in baseball, there's a rectangular slab that pitchers stand on. It is called the pitching rubber. It measures 24 inches wide and 6 inches long. And you can see that pitching rubber on the right side of your screen. So what is the perimeter of the pitching rubber? Now, hopefully some of you have calculators with you. Your computer may have a calculator that you can use, or if you want to really challenge yourself, you can use pencil and paper to try to figure out some of these problems. But what would be the perimeter of the standard major league pitching rubber? Two sides are 24 inches. The other two sides are 6 inches. You just add up all four sides. That's how it goes. So you've got 24 inches, 24 inches, 6 inches, and 6 inches. So you want to just add up all four sides. Well, if we do it right, we should come up with an answer of 60 inches for the perimeter of a pitching rubber. And you can see the illustration up top. So the two long sides, the width actually in this case, 24 inches. And then the two short sides, the length actually 6 inches apiece. Just add them up. 24 plus 24, that's 48. Plus 6 is 54. And then 6 more inches comes to 60 inches. So that's the perimeter. Add up all four sides of a rectangle, you will come up with a perimeter. And for the rectangle, the pitching rubber, it is 60 inches. That is standard, cannot deviate. Can't be 61 inches, can't be 59. It's got to be 60 inches exactly in order for it to meet the standards of baseball. Now, we can also take this pitching rubber and we can figure out what the area of it is. Again, we're talking about rectangles. And for rectangles, we have a basic formula to calculate the area of that shape. It's length times width. Length times width, or width times length, whichever you prefer. So we know that the width is 24 inches. We know that the length is 6 inches. So if we multiply them, we can then come up with an area. You may want to write this formula down. Width times length equals area, or length times width equals area. Same either way. And if you multiply those two together, you will then come up with an area of a rectangle. One of the things that we do when we figure out the area of a rectangle, we will express it in terms of square inches or square feet, whatever the unit of measurement might be. So we take the width, 24, multiply it by the length, 6. When you multiply those two together, you should come up with 144 square inches. So that is the area of a rectangle. The two long sides, they're both the same, 24. The two short sides are both the same, they're 6. So you multiply, you don't multiply all four sides together, no. You just take the length and the width, you multiply those together, 24 times 6, and that will give you a number, and then we express it in terms of square inches or square feet, whatever the unit of measurement might be. And I see some folks correct correctly came up with the answer of 144 before I even told them. So good job out there. Here we have Fenway Park in Boston. We showed you the scoreboard there earlier. It's one of the most famous ballparks in the major leagues. We can not only find squares, but we can find circles. Pitching mound is a circle. Area around home plate is a circle. There's also a couple of circles to either side of home plate. Those are actually called fungo circles. During pregame warm-ups, there's usually a coach who will hit fly balls out to the outfielders. And they do it from those circles. They call them fungo circles. Also, if you look carefully and maybe use your imagination a little bit, you can kind of see circles around third base and kind of around first base. You have to use your imagination a little bit. It's not a complete circle that's formed, but at least a partial circle that we can visibly see. Well, there are elements of a circle. There's the diameter. What is the diameter of a circle? Basically, it's the measurement of a line, straight line, that is drawn from a point on the circle through the middle of the circle and then reaches another point on a circle. Think about it this way. Think about a circle, and you're going to drive a spike through that circle. So you're going to start at an outer point on the circle. You're going to drive that spike right through the middle of the circle, and then it's going to come out to a point on another part of the circle. The distance of that straight line, measured right through the center of that circle, is the diameter. That's what the diameter is. Now, we can also figure out what the radius of a circle is. And that's the distance from the center of the circle to a point on the circle. And you might notice there's kind of a relationship between radius and diameter. The radius, you can kind of tell it visibly here, is half of the diameter. It's half the length of the diameter. In turn, the diameter is double the length of the radius. So there's a specific relationship between diameter and radius. If we know what the diameter of a circle is, we can then figure out the radius. Similarly, if we know what the radius of a circle is, we can then figure out the diameter. So it's kind of good that we can do that. If we know one of the values, diameter or radius, then we can figure out what the other is. Now, there are some formulas for taking measurements of circles. One of them is called circumference. And there's a formula. I'd like you to write this down. It's the diameter times the value of pi, which we sometimes write out as pi. And the value of pi is 3.14. It's actually, in reality, it's a number that keeps going on and on and on. But for simplicity's sake, we refer to it as 3.14. We don't keep going with the digits after that. So the value of pi is 3.14, and that is always going to be the same. But the diameter from circle to circle will be different. And if we multiply the diameter by the value of pi, we can then come up with the circumference of a circle. So here we have a circle, and it has a diameter of 4 feet. So we plug that into our formula. Pi times diameter equals circumference. Diameter is 4, pi is always 3.14. So we multiply those two. We multiply 4 times 3.14, and that will give us the circumference, in this case, in a measurement of feet. So what's the answer we come out with? 3.14 times 4 comes out to 12.56 feet. And just going back to the circle, you know, that outer edge that you see, we're not talking about the diameter for the moment, but the outer edge of the circle, that area around that, that's the circumference. It's kind of measuring, it's almost measuring the perimeter of the circle in a sense. So that's what we're finding out. what is the distance? What is the length of that edge of the circle, that perimeter of the circle? Well, when the diameter is 4 feet, we multiply it by 3.14, which is the value of pi. We come up with a circumference of 12.56 feet. So that's what that is. Now, we also can figure out the area of a circle. That's a little bit of a different formula. We're still going to use the value of pi, 3.14. But now, instead of diameter, we're going to use radius squared. So we're going to take the radius, multiply it by itself, and then we're going to multiply that by the value of pi. So again, pi times radius squared. Okay. Radius squared is not the same as doubling the radius. For example, if we have an 8-foot diameter here, well, we know that the radius is half of that, so that's 4 feet. So in terms of our formula for area, we're not figuring out radius doubled, because that's just going to give us the diameter. No, we're figuring out radius squared. We're going to take the radius and multiply it by itself. So if the diameter is 8 feet, we know the radius is half of that. It's 4 feet. Well, let's multiply the radius by itself. That's 4 times 4. Now we know that the value of radius squared is 16. We then are going to multiply that by the value of pi, which is 3.14. Okay? So we're going to take 3.14 and multiply it by 16, radius squared. What happens when we multiply the two together? We get 50.24 feet. And because we're doing area, just like we did with the area of a rectangle, for the area of a circle, we refer to it as square feet or square inches, whatever the unit of measurement might be. So 3.14 times 4 squared, which is 16, is going to give us 50.24 square feet. And that's the area inside the circle. So again, going back to the circle, the circumference is the distance around the circle, kind of the perimeter of the circle. But the area is inside, that area inside the circle. And that's what we've just figured out. So we take the radius, we square it, then we multiply it by the value of pi, 3.14, and we come up with an area of a circle, 50.24 square feet. So that's how we do it. So just to kind of review some of the formulas, for circles, the area is pi times radius squared. Circumference of a circle is pi times diameter. For rectangles, area is length times width. And the perimeter for a rectangle, you just add up all 4 sides. So those are the basic formulas we're working with. Now, I want to introduce something else as well here, and this is a little more advanced. Some of our younger viewers may have a little trouble with this, but some of our students who are a little bit older, maybe 7th, 8th grade, high school, can probably grasp this pretty well. So we have Progressive Field in Cleveland. We've seen that there are circles and rectangles on a baseball field, but if we use our imagination, we can also find triangles. Look here. We see the distance from home plate to first base. That's one side of the triangle. Distance from home plate to third base. That is the second side of a triangle. And then if we draw an imaginary line from third base to first base, we have a third side of a triangle. Now this happens to be a right triangle, where you have a 90-degree angle. And that 90-degree angle is formed between the first base and third base lines, 2 sides of the triangle. Well, that third side, which we kind of imagine here, we have to draw it in because it's not actually spelled out on the baseball field. That third side is the hypotenuse. That's the side that's opposite the 90-degree or right angle. And in baseball, we can actually use triangles to determine the length of a batted ball. And we can do that with something called the Pythagorean Theorem. And again, I'd like everybody to write this down. A squared plus B squared equals C squared. A squared plus B squared equals C squared. The Pythagorean theorem applies to right triangles, like this one we've drawn onto Progressive Field in Cleveland. Now, basically what the theorem says is this. If I know the value of two of the sides of the triangle, then I can always figure out what the third side is. So if I know the value of A and I know the value of B, I can then figure out the value of C, which is the hypotenuse. Similarly, if I know the value of A and I know the value of C, the hypotenuse, then I can figure out the value of B. Similar to that, if I know the value of B and I know the value of C, then I can figure out the value of A. So as long as I have the values for two sides of the triangle, then I can figure out the third side. Now, if I have only the value of one side, that's not enough. I need to have the value of two sides, and then that will allow me to figure out the value of the third side. So, using the Pythagorean theorem, let's determine the length of the hypotenuse of this right triangle. And again, the hypotenuse is that long side that's opposite the right angle. So that's C. That's what we're looking for. Now, we know the value of one side, A, is 3. So that's that vertical line in the triangle we see here. We know that's 3. Then the horizontal line toward the bottom of the screen, we know the value of that. It's B, and that's 4. So I know the value of A. I know the value of B. Now I should be able to figure out the value of C. Just plug the numbers into the formula. A squared plus B squared equals C squared. So if A is 3, what is A squared? That's 3 times 3. That's 9. If B is 4, what's the value of B squared? Well, it's just 4 times 4, and that's 16. So now I know that A squared is 9, B squared is 16. If I add them together, I come up with 25. And that is the value of C squared. The value of C squared, 25. But we need to figure out the value of C. That's the square root of C squared. We need to figure out the value of C. Great thing about calculators is that they have a square root function. And if you put in the number 25 and use the square root function, you can figure out what that square root is. And hence you can figure out the value of C. So let's see what happens here. We have A squared plus B squared equals C squared. So 3 squared is 9. 4 squared is 16. Add them together, it's 25. That's C squared. The square root of 25, we use our calculator, comes out to be 5. 5 times 5 equals 25. So we know that the value of C is 5. So we go back to our triangle, our right triangle here. We know that if A is 3, B is 4, then C has to be 5. Now, it could be inches, could be feet. We haven't specified the unit of measurement. But if the value of A is 3 and the value of B is 4, then the value of C has got to be 5. That's how it works. All right? So that's a little more advanced than some of the other stuff that we talked about earlier. And actually, we can use this to measure the length of a home run. Let's use Derek Jeter, part of our Hall of Fame class of 2020. Let's say Derek Jeter hits a home run to straightaway center field in Yankee Stadium. The ball clips the top of the wall and lands in the stands. If the distance from home plate to the center field wall is 408 feet, and that center field wall stands 10 feet high, how far did the ball travel? And you'll see on the right side of your screen where the photo is, we've kind of drawn a triangle, an orange triangle there. So looking at this triangle, we've given you the value of two sides. The distance from home plate to the wall, that's kind of the bottom part of that triangle there, that long part. We know that's 408 feet. And then the distance from the base of the wall to the top of the wall is 10 feet. So let's say the 408, we'll say that's A. So we're going to square it. We're going to multiply 408 by 408. This is where it's helpful to have a calculator with bigger numbers. We're then going to take the value of B, which is 10, the height of the wall. We're going to multiply 10 by itself. So we know 10 by 10 is 100. That one's easy. Those who have calculators can quickly figure out what 408 times 408 is. Once we've done those two things, we have the values of A and B, and then we can figure out the value of C. And that's the hypotenuse. That's that long side of the triangle that goes from where Jeter hit it to the very top of the wall. That's the actual distance of the home run. So this is how we're using Pythagorean Theorem. This is how we're using triangles to measure the length of a home run hit by any player. Let's plug in these numbers, see what we come up with. A squared plus B squared equals C squared. So it's 408 squared 408 squared and then added to 10 squared. What's 408 times 408? Well, it's a big number. 166,464. What's 10 times 10? That's a little easier. That's 100. So we then add those two numbers together, A and B. We add them together, and it comes out to 166,564. So that is the value of C squared. But we want to know the value of C. That's the distance that Derek Jeter's home run ball traveled. Now, to try to figure it out just in our head, the square root of a big number, that's pretty hard to do. Most people can't do that. I certainly can't. So this is where it helps you have your calculator. But you put in 166,564, use the square root function on your calculator, and you will come up with a number of 408.12 feet. So the distance from home plate to the base of the wall was 408 feet. But Jeter's home run, it's elevated a little bit because it's got to clear the wall. It's got to hit the top of the wall and then bounce over. And that's a little extra distance. That's where you get the extra 0.12 feet. So the value of C, the distance of that home run ball Derek Jeter hit, is 408.12 feet. And that's how we can determine the distance for any home run ball that is hit. So that's Pythagorean Theorem. All right, in our remaining minutes, we're going to have some fun and play Circling the Bases Home Run Derby. Normally, when we do this with school groups, I take half of the classroom and I make them the red team, and I take the other half and I make them the blue team, because everybody is from remote locations today. We're not able to kind of do that. We don't have teams. We can't set it up that way. But individually, we're going to give you a few moments to try to tackle each question and see if you can come up with the right answers using the geometric concepts we've talked about. So let's begin with our first home run derby question. The sports of baseball and cricket, which is very popular in Great Britain, have similarities and differences. The actual field of play is one of the distinct differences between the two games. Baseball, as we said earlier, is played on what we call a diamond, even though really that infield is a square. Cricket is played on what can best be described as a circle. And you can see that in the image on the bottom right of your screen. So if the field of play for a cricket match has a 35-foot radius, what then is the diameter of the field? Remember, the radius, you draw a line from the center of the circle to a point on the edge of the circle. That's 35 feet. What then is the diameter of a regulation cricket field, a sport that is very popular in England? We talked earlier, there is a relationship between radius and diameter. If I know what the radius is, I can then figure out the diameter. Similarly, if I know what the diameter is, I can then figure out the radius. Well, we know that whatever the radius is, the diameter is going to be 2 times that. So we're going to take 35 feet. We're going to then multiply it by 2. That's all we have to do. So if the radius of the cricket field, that circle, is 35 feet, then the diameter is going to be 70 feet. So we multiply 35 times 2, and we come up with a diameter of 70 feet. Now, if I had told you what the radius was, if I had said, hey, the radius of this cricket field is 35 feet, or I'm sorry, if I had told you what the diameter was, if I had started by telling you the diameter was 70 feet, and then I'd asked you to figure out the radius, you could have figured the problem out. All you'd have to do is divide the diameter by 2, because the diameter is double the radius. So if we started with a diameter of 70 feet, you then divide it by 2, you'd then come up with your radius of 35 feet. Works either way. So that was our first question. I'm sure most of you, if not all of you, got that right. All right, next question. And I got to move my chat box because it's actually obliterating part of my question here. All right, now I can see it better. Given that each on-deck circle has a diameter of 6 feet, this is a standard Major League on-deck circle, what then is the area of the standard Major League on-deck circle? So each on-deck circle has a diameter of 6 feet. What then is the area of that on-deck circle? So we need to go back to our formulas. We're trying to figure out area of a circle, and that is pi times radius squared. Pi is 3.14. Well, the diameter is 6. I didn't give you the radius, but I know the radius is half of the diameter. So 6 divided by 2 is 3. So now the formula reads 3.14 times 3 squared. 3.14 times 3 squared. Give you a moment here to figure it out. When we're squaring a number, we're multiplying it by itself. So 3 times 3, and then we take that number, multiply it by the value of pi, 3.14. Hopefully, you'll come up with the correct answer. And the answer is 28.26 square feet. Some of you got that correct answer very nicely on the chat. Good job. So 3 squared is 9. Radius squared, 9. Value of pi, 3.14. Multiply 3.14 times 9. We come up with 28.26 square feet. Because it's the area of a circle, we use square feet, square inches, whatever the unit of measurement might be. All right, let's move on. While batting, a player must stand in the batter's box. The batter's box is a rectangle, and it measures 4 feet by 6 feet. What then is the perimeter in feet of a standard Major League or minor league batter's box? It's the same both Major League and minor league ball. Batter's box is a rectangle measuring 4 feet by 6 feet. What is the perimeter in feet of a batter's box? Now, this was the very first formula we went over. Perimeter, you add up all 4 sides. We know that one side of a rectangle is 4. So then there's another matching side that's also 4. And then you've got 6 feet, but there's another matching side that's also 6 feet. So there's 4 sides. So we'll take 4 plus 4 plus 6 plus 6. That is going to give us the perimeter in feet of a batter's box. And I'm sure pretty much most of you, if not all of you, came up with the answer. Add up all 4 sides. 6 plus 4 plus 6 plus 4. 6 plus 4 is 10. Plus 6 is 16. Plus another 4 is 20. You could mix up the numbers in a different way. You could have done 6 plus 6, which is 12. Plus 4 is 16. Plus 4 is 20. Either way, going to give you the same answer. So the perimeter of a standard major league batter's box is going to be 20 feet. That cannot vary by a centimeter. It's got to be exactly 20 feet if it's going to meet the regulations, the standards of a professional baseball field. All right, here's one that you don't really need a calculator for. If you were paying attention to our earlier part of our lesson, you heard me talk about this. Home plate is traditionally a slab of rubber with 5 sides. What geometric shape is home plate? Well, we've talked about triangles. We've talked about rectangles. We've talked about circles. What is a 5-sided shape? Those who paid attention know it is a pentagon. It's really the only pentagon you'll find on the baseball field, and it is home plate. 5-sided shape, pentagon. All right. Here we're going to talk about the baselines a little bit. Hall of Famer Rickey Henderson holds the record for career stolen bases with 1,406. If Rickey takes a 10-foot lead off of first base, how far does he have to run in order to steal second? Now, we did talk about the distance between the bases earlier. In case you forgot, it's 90 feet in between each of the bases. So it's 90 feet home to first, 90 feet home to second, 90 feet second to third, 90 feet third to home. All 4 the same. So Rickey's at first base. He takes a lead of 10 feet. How far does he have left to run in order to steal second? So we start with 90 feet. We then subtract 10 from that. We'll come up with an answer of 80 feet. So the longer the player's lead is, the shorter the distance remaining to run to the next base. Of course, the tricky part is if you take too big a lead, the pitcher could pick you off. But a 10-foot lead now means that the base stealer has 80 feet left remaining to run to try to beat the catcher's throw. Another question for Homerun Derby. A right-hand batter hits a foul ball into the first base dugout. Using the third base line as a guide, and given that the first and third base lines form a 90-degree angle, did this ball travel at an obtuse angle or an acute angle? Obtuse angle is an angle greater than 90. Acute angle is an angle less than 90 degrees. So again, right-hand batter hits a foul ball into the first base dugout. Using the third base line as a guide, did the ball travel at an obtuse or an acute angle? Sometimes with problems like this, it helps to draw some lines onto a playing field. So let's draw where that foul ball went into the dugout, and then let's draw the third base line. Look at the relationship of those 2 lines to each other. Does that form a 90-degree angle? Does it form an acute angle less than 90 degrees? Does it form an obtuse angle more than 90 degrees? Well, when you see it visually, makes it a little easier to answer the question. And yes, it is an obtuse angle because it's clearly more than 90 degrees. The angle of the foul ball in relationship to the third base line. That is clearly more than 90 degrees. So it's an obtuse angle. All right, let's try a question that Might be a little bit more challenging, but I think you can handle it. The left field foul pole at Busch Stadium, home of the St. Louis Cardinals, is 336 feet from home plate. How far would the left fielder have to throw the ball to nail a runner at home plate if he catches the ball exactly halfway down the left field line? So a ball is hit down the third base or left field line. The outfielder, the left fielder, picks up the ball on the line at a point that is exactly halfway down that left field line. So how far is the throw to home plate? Let's think about that for a moment. What do you think we come up with? Well, if it's 336 feet from home plate to the left field foul pole, and the left fielder picks up the ball halfway of that distance, we take 336 and we are then going to divide by 2. And that's going to give us 168 feet. So that's the length of the throw the left fielder is making from that left field line to home plate. It's half the distance of 336. So 336 divided by 2 comes out to 168 feet. All right, let's do one more question, but I'm going to make this one a little more advanced. Jumping ahead a little bit. All major league pitching mounds have a diameter of 18 feet. Given that there are 30 major league teams, what is the combined total area of all major league pitching mounds? So mounds are circles. What's the formula for the area of a circle? Pi times radius squared. Pi times radius squared. So diameter is 18 feet. Half of that is 9. That's the radius. What's 9 times 9? 81, right? So we then multiply that by 3.14. Then we have to take that number and multiply it for 30 teams. So this one's a little tricky. I'll give you a little bit of time to work on that. All major league pitching mounds have a diameter of 18 feet. That means the radius is 9. Given that there are 30 major league teams, what is the combined total area of all pitching mounds in the majors? Again, the formula for area is pi times radius squared. So 3.14 times 9 squared. Let's see what we come up with. So it's 3.14 times 81. Area of one mound is 254.34 square feet. But we want the area for all 30 together, so we multiply 254.34 square feet by 30. We then come up with a total of 7,630.2 square feet. So that is our correct answer. And as the phone rings in the background, that is a signal that Homerun Derby has come to an end. What we're going to do now, we are going to take your questions via our chat box. So if you have questions, just type them in. I'll do my best to answer them. They could be questions about what we've talked about today with geometry. It could be questions about the Hall of Fame, questions about our museum, about how players become Hall of Famers, anything like that. So give us some questions and we'll try to answer them as best we can. Again, you have a chat function. A lot of you have been using that. Let's see, Aaron wants to know, what is the largest baseball field? That is a great question. Obviously, the infields are all standard because they're 90 feet between the bases, 60 feet 6 inches between home plate and the pitcher's mound. But in baseball, the outfields are all different. Every major league team has different dimensions. They have like certain minimums. It's supposed to be ideally 330 feet down the lines and at least 400 to center field. But even those, they tend to vary a little bit. Sometimes ballparks have to be fit into city blocks, and there are problems like that. I'm trying to think what would be the biggest ballpark in terms of the outfield area. Might be Comerica Park in Detroit. I know it's well over 400 feet to center field. And then if you're looking, you might be asking the question in terms of which has the biggest seating capacity. Which ballpark has the biggest seating capacity? I think, if I'm not mistaken, it's Dodger Stadium, where the LA Dodgers play. I want to say it's around 56,000. I think that's the biggest today. It's not the biggest in history. There have actually been major league games played in some parks with over 100,000 seats. But in terms of today, I believe it's the Dodgers. And as far as the outfield area, I think Comerica Park is pretty darn big. Yankee Stadium also has a big outfield, especially towards center and a left center field. So those tend to be some of the bigger fields or outfields. Let's see, Knox wants to know, do you like the new Yankee Stadium or the old park? It's a great question. I've actually not been to the new stadium. There have been three different incarnations, if you will, of Yankee Stadium. The original was built in the 1920s. And then they renovated that ballpark in 1974 and 75. I actually went to a game in 1973, which was the last year of the original Yankee Stadium. And I went to games at the renovated Yankee Stadium. So I did go to games at the first two. I have to say, I probably like the original stadium. The way the facade was in the outfield, and there was just a certain aura to that ballpark, a certain feel there. But I really like the original Yankee Stadium. I have not been to the new one, which was built around 2007, 2008. Haven't been there. I mean, it looks nice on television, and I've heard people that have gone there that say it's nice. They say there's a lot of things going on, a lot of restaurants, there's a lot of activities that kind of go on around the game itself. But I have not yet been there myself. All right. See if some other questions here. Who threw the fastest pitch in Major League history, and how fast was it? I believe the record holder, if I'm not mistaken, is Aroldis Chapman, now the reliever for the Yankees. He threw about 105 miles an hour. Prior to that, Nolan Ryan had the fastest recorded mark speed for a fastball thrown. But I believe Chapman, in terms of recorded pitching speeds, I believe he is the record holder now. Certainly Chapman and Ryan among the two hardest throwers in the history of baseball. Take questions for just a couple more minutes. If you have them, just go onto your chat function and fire away with your questions. I'll do my best to answer them if I can. Let's see, we have a question. Dan from Auburn wants to know if you like the old Cleveland Stadium or the new one. Well, the old one was Municipal Stadium. I never was at a game there, but I've heard from people who went to games there that it was very big and dark and kind of cold. There was a wind that blew in off the lake. So I think the newer stadium is generally considered the better one. And I have been to the new ballpark. It's called Progressive Field now. It was Jacobs Field when I went there a number of years ago, and I thought it was beautiful. I thought Jacobs Field was terrific. Again, now it's called Progressive Field, smaller than that old stadium, not as cavernous, much more comfortable for the fans, so a really, really nice ballpark. All right, I think that's it in terms of our questions for the day. We want to thank everybody for your questions. Thank everybody for joining us today. We're going to do another one of these programs in a week about the history of women in baseball. That'll be a lot of fun. And also a reminder that coming up tomorrow, Friday morning, 11 a.m. Eastern Time, it'll be our next virtual Voices of the Game. We're going to talk to a great baseball writer and a terrific guy, Jason Stark. And that'll be from 11 a.m. to 12 noon Eastern on Friday. Thanks for joining us for Circling the Bases Geometry at the Baseball Hall of Fame in Cooperstown. Have a great day, everybody. Bye-bye now.